So Peng is a principal research statistician developer at JMP. He holds a PhD in statistics from NC State, and he's been working at JMP since 2007. So he specializes in computational statistics, software engineering, reliability data analysis, reliability engineering, time series analysis, and time series forecasting. If you've used any JMP features related to any of those, this is the guy who helped develop them. So he has a broad interest in statistical analysis research and software product development.
Thank you, Caleb. Thank you. Yeah, as Caleb introduced me, I'm a statistician by training, but I'm also half statistical, half of software engineer, so it's half. And by training, I was specialized in time series when I did my PhD. I picked up the reliability after I started working with JMP, so that's been 15 years. And for the topic today, I'm going to cover Bayesian methods, but I am a frequentist by training. So I'm picking up other things that I didn't know before. So I'm all along the way that I'm learning, and I'm glad that I have opportunity to share with you what I have learned and have developed, and how JMP can serve what you need for your work. So at the request of the organizer of this conference, I'm going to provide a brief tour of JMP reliability platforms for the maybe first half, 30 minutes. Then I will switch gear, go direct into the Bayesian method for reliability data analysis. So can I ask first question, how many of you have not heard about two terms? One is viable analysis, and the other one is accelerated life test. If you haven't heard about these two terms, can you raise a hand? Okay, good. So it might be bumpy road for you guys if you haven't heard it. I will try to explain, give you a good foundation at the beginning, so you can catch up. And but the gap between that foundation to the Bayesian analysis, the gap is pretty big. And yesterday I attended a short course. Yesterday, they taught Bayesian approach in a general sense. They offered a course for the entire day, and it's pretty good. I went there too as well and learned different perspectives from what I learned. So what should I offer today in a different perspective? That make me think about it. So if they offered yesterday is a way to teach you how to catch fish, what I'm going to show you today is how to let you know you are going to a restaurant, know what you want. I'm going to teach you how to place your order. All right, so this is a very major difference. Yesterday's short course was awesome. That's if you have a chance, take it. Go ahead, take it. If they offer it next year, go ahead and take it. They offered a general approach of how to apply these methodologies to the new spectrum of problems, and they can solve a lot of problems. And I will share my experience with you later towards the end of the tutorial. So let me first build a foundation for some of you that are new to reliabilities. So I list some of the example questions of interest. What kind of question people will ask if they are going to analyze reliability data? So the first one is, what's the time to failure distribution of light bulbs? Think about Thomas Edison. When he invented his first light bulbs, if the consumer have to switch the light bulbs every other day, they probably won't buy it. So Thomas Edison knew to figure out, okay, how long my light bulb can last. But how long it can last, it's not a deterministic number. He cannot say it. My bulb will last for a week if we put it on. He cannot say that. It's a random number. It's a random quantity. So to describe random quantity, statisticians use distributions. So the time to failure distribution is a way to describe the life of a light bulb that Thomas Edison will commercialize, marketing it. So second example is when to replace a turbine engine blades. The turbine engine blades is spinning all the time. It gets pressured by the gas. Over the time, the blade is switched to metal alloy or metal. What kind? I don't know. I'm not know about these things, but it's metal. I know. Over the time, because of air pressure, it will bend. It will vibrate. Over time, it will get fatigued, and it will develop crack. And the crack can't be too long. If the crack is too deep, it's not safe to run the turbine anymore. You have to replace the turbine. The question is, when should you replace the turbine blade? Because the crack length growth is a random process. We cannot determine, say, you need to replace, the turbine blade will fail in 10 days. You cannot say that. It's a random number. It's a distribution. So this is another second question. The third question, the third example is, what's the drug expiration date? If you go to doctor prescribe you something, and there's a label on, I'm not sure where they all have that, but at least the aspirin, like over the counter, the bottle, it will say expiration date. Oh, our food has expiration date, right? How do they decide that number? So this is also a case. How do we put the label of the expiration date on that package? And this quantity is determined by some kind of random phenomenon. And they did not pull from the thin air to put a number on that label. They had to do some kind of analysis and study the distribution when the food will go spoiled, and put a single number to make it easier for consumer to determine whether they feel it's safe to buy or not safe to buy. And they put a single number on that label. But that single number come out from a study of the distribution, the time to spoil. Well, let's see what's the next one. When to replace undersea optical fiber cable. When the cable, optical fiber cable is under the Atlantic Sea, you don't want to replace it every year. But this cable, because the pressure and the other things that I don't understand, and also because we are running signals through these fibers, and even its fiber, it's pretty reliable thing, but it over time can degrade. When it's degrade, when do you need to replace that cable? That's another question. And that phenomenon is also random. They have to study the variability of the cable goes bad. Let me see what's the next one. It might be interesting. How many thermal aging devices in the stockpiles are bad now? And I will have an example later. So the device, like integrated circuit board, and if you put in a harsh condition and run it outside, in the winter it's cold, in the summer it's hot, so it's contract, expand, is thermal cycles. And over the time, this kind of device can just will go bad. For example, the soldering iron will get loose, and all these kind of issues with that. And they will be interested in, because these devices are in a stockpile, you don't check that often. But when you pull it out, start to use that, suddenly if you find out this device doesn't work because of thermal cycling. Now the question is, how many of these devices are bad in your stockpile? So these are the questions that we will ask that relate to the reliability data analysis. So last bullet point. So here, there are formal definitions. For example, I will mention later there's a reference that we use that's very often, and I rely on that for development very much. So in this book written by William Meeker, there are formal definitions there, but pretty long, 3 lines. And there are short ones, but you can check them. But for this tutorial, I'm going to emphasize this. Remember this. Most of the time, not all the time, is the study reliability data is to estimate a time to failure distribution. You are actually want to estimate a distribution, entire one, not the mean, not the standard deviation of a normal distribution. You want to study the entire distribution, and this distribution can be different kind. So remember this, for this tutorial, the purpose of studying reliability data is to estimate time to failure distribution. Sometimes it's not time to failure, it's time to event. But for this tutorial, just remember time to failure. When the food goes spoiled, when the light bulb goes out, and these kind of things. And also, this distribution, it can be the entire distribution. You might be interested in the entire distribution from the tail to tail. Or you might be just interested in part of the distribution. For example, the first half of the tail, first half of the distribution, or the later half of the distribution, maybe just partial of it. Or even you might be interested in the distribution you will never observe. I will have an example about what this means. So thinking about what you know right now is if the distribution you cannot observe, what can you do about it? So it's a tough question. And this is part of the mission that we need to tackle. That's when we study reliability data. This is the book I mentioned that's written by Meeker and William Meeker and his co-authors. So this is the second edition of his book. First edition published in maybe 20 years ago. So the title is Statistical Methods for Reliability Data. I have been with JMP for 15 years. Over these 15 years, I collaborate with Dr. Meeker very closely. And we get his advice, his suggestion about what we should develop and what method we can use, because there are not only one method out there to analyze one particular data. There are some competing methods. So we listen to his suggestions and follow his suggestion of prioritize our development. At the beginning, 15 years ago, we had 3 platforms: survival analysis, parametric survival, recurrence analysis. Oh, and an extra one, that's Cox modeling, but that's not very frequently used as reliability data analysis. Since then, we add more and more and more, and now we have over a dozen platforms. As I mentioned, that the focus we study reliability data is to get the distribution. I put that in the center of this graph, this life distribution. It's also the name for one of our platforms. So from this distribution, one of the goals is to estimate this time to failure distribution. But to estimate this distribution, we need to get starting from somewhere, how to get the data. So at the bottom here, these are some of the related products that we provide to get you a starting point. And for example, that's you need to design something to collect your data, run experiment. There are different kinds of experiments. You can just do a simple life planning, so there's no other extra covariate or factors that you need to be involved. You just put a light bulb on the socket and let it burn. So that's one type of experiment. Or it can be ALT data and design. ALT stands for accelerated life testing. For this type of design, you usually put the experiment unit under different conditions, for example, different temperatures, or different voltages, or different humidities. And the purpose of that is that if you just run an experiment under the regular conditions, the use condition, the product is so reliable, you will never find out any failures. And I will mention that why observing failure is so important, and that's why we need the Bayesian approach. If in a situation that you run an experiment and don't get any failures, the data that you have contain very, very little information about this distribution you want to estimate. So you want to get failures. And ALT design, accelerated life test, is a way to get your failures under an accelerated condition. For example, high humidity, high voltage, high temperature. Then you backtrack, then to extrapolate your estimates from the higher end of the use condition and derive the distribution at use condition. That's what I mentioned earlier, that the distribution you can't observe at use condition is what you are really interested in, but you want to be able to observe it under the regular condition. All right, so that's the second part of the second way of getting some data that you can estimate the distribution. The third one, degradation data. For the first two, we are recording the time to failures. Those are the data we get. There are other situations you can observe more. Degradation, that you can actually trace how this thing go bad from the beginning to when it's end its life. So you can actually trace its performance over time. So this type of data give you more information, and sometimes it's even more useful. All these kind of situations provide you different kind of data, and in the end, you want to analyze it in different ways. The ultimate goal is still to get the distribution. Then what? Then you can use this distribution, your estimates of distribution, to get to other things. For example, the warranty analysis. You can estimate of your car engine, the time to failure distribution. Then you can put a warranty tag on your at the dealer shop. So hey, we provide this powertrain protection to you for 3 years for free. Then they will try to sell you an extra a warranty. Why do they want to do that? Because they know what's the time to failure after 3 years. I'm not sure how they price it. That's not my specialty. I think the actuarial those statisticians also they are specialized in those subjects. They will put a price tag on these things, but fundamentally they need to know the time to failure distribution. So if you get the failure distribution, you can do other things. First thing, the warranty analysis. Also, you can study the system design things and get a so-called system reliability. What I'm here saying is distributions are usually very simple, like Weibull distributions, log normal distributions. Even sometimes you can use normal distribution. The difference between normal distribution and the other distribution I mentioned is for normal distribution, the value of the variable can go negative, but time to failure is always non-negative. So this is the difference. But sometimes you still can get away using normal if it's a good approximation to your data. Most of the time, you just use log normal and Weibull. That's in majority of situations. But these two are very simple distribution. They want to be able to describe all kinds of failure distribution we observe. For example, the system's reliability. You can describe the car brakes life time to failure distribution using, say, a pretty simple distribution like log normal. The time to failure of a car is a much complex question to ask. So this is why we study the system reliability. By studying system reliability, we construct a system, and there are different components, and each component have their individual life distribution. Then you try to come up the assembled life distribution for this system. So this is why how we get from here, life distribution, to all the way to this system reliability. So I listed all these platforms under the name JMP reliability products for non-repairable things. You realize that these things we are describing, have been describing here are not reliable. Light bulbs, medicines, the food expiration labels, they cannot, we cannot put the spoiled food back to as a fresh condition. And here are the list of these platforms that's dedicated to analyze this type of reliability data. And you need all these kind of things is because we can all kind of different situations to observe them, run experiment to collect data, and also it has different kind of applications. So we need all these kind of tools to fit different kind of situations. Now, this next slide is JMP reliability product for repairable things. This is not emphasized today, and I want to go that very quickly. But I want to mention that its application. 2 examples. First, you maintain your cars. You send your car to the dealership every, say, 3,000 miles. That was criteria 10 or 15 years ago. Now they may be 4,000 miles. You need to regularly send your car to the dealership to maintain it. How do they come up with this number? They study this repairable system's reliability. And they said, if you don't come to our shop every 3,000 miles, 5,000 miles, your engine will go bad pretty quickly. And if you don't come to us in 3,000 miles, we cannot guarantee your car won't be damaged after 2,000 more miles without maintenance. So this is the one example. That's car maintenance. Car is a repairable system, and they studied that. Another example is probably related to this institute. You have contract with your suppliers, develop a weapon system or something like that. Tom may have more to say about that. When they develop a new program, they have to demonstrate to this institute or maybe some whoever asking for that development, they need to demonstrate is this new development is reliable to guarantee some stability about this new weapon systems development. So they observe how often you improve your design to meet the goal. If then there's empirical evidence that if you develop some new product or new project or new weapon system, you will find problems, then you fix it. You find out the problem, you fix it. Over the time, if you measure the time gap between two incidents, every improvement, you'll find this gap getting longer and longer and longer. That's improvement over performance. And this kind of type is also a subject of reliability data for repairable systems. If you can eventually say, I'm very comfortable for my new development, because you see, last time I improved that was 3 months ago. We haven't had any incidents for 3 months. So they then can put a number there that's about their confidence. So this is some of the application for reliability data analysis for repairable systems. And this is a list of the things that I mentioned as we have all, let me see. So we can classify our platform in different ways. First is we can classify as a non-repairable system. This is this section, first section, and all the repairable system, which is section at the bottom. And in the second column, I have all these different JMP products or JMP platforms. That's what we call them. And they are designed to address different situations, which is listed in the third column. If we just have time to failure data, we use life distribution. If we have the time to failure data with one time invariant factor, say temperature, then we need to chase after this platform. It's called fit like by X. And because the first platform won't be able to solve this problem, won't be able to analyze this kind of data. If you have time to failure data, and you have only one acceleration factor, but the setting of the factor changes over time. For example, you run experiment and the acceleration factor is voltage, but the voltage change over time. You started setting low, but over time you did not observe failures, but you want to see failures. You increase the voltage. After a while, you still haven't seen any failures. You increase it again. So this variable is changing over time. For this kind of situation, even the fit like by X platform won't be able to help you. You have to check out this platform. So all these platforms are designed for specific situation you have. Let me see. Okay, the third one, the parametric survival. This platform is designed for time to event with multiple time invariant factors. You can have voltage, you can have humidity, but at the same time. Then you have to use this product, parametric survival. Let's see, what's this? Repeated measures degradation. So this is designed for situation you have degradation data from non-destructive experiment or observations. So all these platforms are designed for very specific use cases. And this is the entire list we have. And let me see what's the next one. So this slide is saying that within each platforms, we have different models. You might already be overwhelmed by the number of platforms we have here. But within each platform, we have different models. So what does model mean? Model means different things to different audience. You talk to engineers, you talk to the architectures, they all talk about model. What that model means, they may mean different things. So in life distribution, numerous distribution types are provided, and each distribution type is a model. And also support competing causes. I'm not going down deep that rabbit hole, but that's another model. Mixed distribution, that's another model. So life distribution, it has at least more than another model there. Fits life by X. So and the cumulative damage, we provide numerous distribution types and different acceleration mechanisms. So I'm already mentioning that distribution type is a type of model, but here for acceleration life testing data, the mechanism is also a way to differentiate different model from model. How the voltage accelerates the failure is different from the mechanism, how the temperature accelerates the failure. So they are depend on different, I say, physical theories, something like that. So there are at least, if I remember correctly, at least 8 different models on the fit life by X and cumulative damage. Repeated measures, degradation, and destructive degradation, I say different degradation mechanism. The path I described, you can measure over time, the shape, how fast it go bad, all these defined by some type of model. They are different from one to another. For the last two, they are for the repairable systems, and there are different ways of describing these repairable systems. It's mainly describe how the time gap change from time to time, and those are different models. Tom?
Just want to point out the last one there, reliability growth. Pong has created an add-in called the Reliability Growth Planning add-in, where he's basically taken the work of the folks at AMSA and the mil-spec handbook guidelines for doing reliability growth planning. So if you are at all familiar with the work at AMSA, they've got a large group of people there doing reliability growth planning. He's made a way to implement that, but you have to do it with an add-in that you can download from our JMP community.
Let me repeat. Let me first repeat what Tom said, and then go with you. Okay, all right, go ahead.
Is it continuous and discrete?
The data itself is discrete. The data itself is discrete, so you record the time to event, also time to event, but you that had event over time, so you have discrete observations of event. But the process itself is continuous.
Okay. Maybe okay. So Mill Handbook 189C, right? The reliability growth planning has right. So there's equipment that's continuous time to fail. That there's a whole reliability growth methodology for, right? Like Crow model and things like that. Then there's the discrete use, like single shot, like flight test based, like binary success failure that has its own, the PM2D. There's PM2C and PM2D. Do you have both in JMP?
Let me first start with repeat what Tom said. Tom mentioned that I developed an add-in in JMP that which will implement one of the Mill handbook on reliability growth planning. And to my understanding, even I developed that, but to my understanding, that is not a data analysis utility. That's very much like a calculator, to my understanding. So for the sake of relevance to this talk, I'm not going to go there. But as Tom had mentioned, this add-in and this subject is very related to the conference here and related to DoD. But if you want to explore that direction, that you can contact me or contact Tom Donnelly.
All right. Thank you.
That was my question as well.
All right. Okay. So let's pretend that I don't know that. Let's move on. So it's 2 o'clock. Let's see. Oh man, I may not have enough time. Okay. So just to impress you guys, this all kind of screenshot I put together that's represent my work for 15 years, and this maybe just half of it. Let me move on. Okay. Now we move down to our main focus, the Bayesian method for reliability data. If you went to yesterday's short course, they probably very much covered these slides. They say, if you have very limited information in your data, Bayesian methods can help you. And this is the case here. So reliability data can be scarce. As I mentioned, if you don't observe failures, there are very limited information in your data. How come? Why is this reliability can be scarce? We live in a big data age. Well, how come the reliability can be scarce? Because we want to observe failure observations events, but sample size can be small. If you want to run an experiment, we don't have a luxury to collect 1,000, maybe 10,000 units to run them parallel and to observe failures. The cost is high. So sample size can be small. Sample size can be small. A portion of it can be possibly to fail. Then what can fail is limited. Also, the experiment duration can be short. Remember that we are studying the time to failure. We actually had to put in time in it to observe failure. We cannot say, press a button to see whether to fail or not fail right now. We can't do that. We have to wait. But the time duration is a limitation for our experiment. If the duration is short, we don't have much time to observe failures. So the failure rate can be scarce. Also, as the subject can be very reliable. And so the duration of experiments is relatively short. We want to be able to observe failures. So when data are scarce, conclusion on reliability can be unrealistically conservative. That means if we have little failure there, the conclusion get using a normal approach is probably conservative, means your actual situation is better than that. But how to back up your assertion? You use some other method. Bayesian is one way, and it provides a formal way that you can defend yourself about your conclusion. Bayesian method can incorporate additional information. If the information is trustworthy, and conclusion on reliability can be more realistic. And the instructor yesterday and give you examples of how these things can improve your inference based on limited information in the data, plus the expert opinions on the prior that can put it into the model. The challenge is how to get trustworthy information. You have heard a lot of argument yesterday. I'm not going to too deep go there. I will leave it to them. Okay, this is something maybe different from what they offered yesterday. Reliability model can be challenging due to nonlinearities. Or the mixed effect. You will see example of mixed effect later. And also censoring. I will mention censoring later if you are new to reliability data. If you combine all these three, to my knowledge, there are no methods out there can give you a good answer. They can approximate, but how good the approximation is, that's questionable. But the Bayesian can provide a very rigorous approach to get you some point somewhere. So for this situation, it's challenging to fit these type of things using traditional statistical inference methods. And there are competing traditional statistical inference methods, and it's difficult to justify or evaluate their differences. So these are the challenging if you have all these situations combined, and we actually have either reliability data analysis situation. And Bayesian method provide a unified approach without any ambiguity. There are no other way of doing Bayesian approach in second ways. You have only one way doing it. And it's flexible without need to invent some other new wheels for the new problem. A challenge is it requires a lot of computation power and a steep learning curve. And I'm learning that too. So this is the plan. I'm going to go through my examples using JMP. I'm doing the demonstration live. But before that, we need to have agreement on the data format. If we are new to reliability data, what you need to know is about the censored data format. Censored data formats. So what is censoring? Let me see. Let me first summarize. What are the censoring types? There are 4 types here. First is failure. Failure means you know the time it fails exactly. No more, no less. So that's exact failure. Second one is called right censoring. Right censoring means if you say this light bulb as example, it has been installed for maybe 5 years, it's still on. What's its failure time? It's larger than 5 years. We don't know it will fail. Eventually it will fail. For this particular light bulb, its censoring time is 5 more years. We don't know. If we recorded 5 years, this 5 is right censored. Okay, the third one is left censored. It's the opposite of right censored. If the 5 is the time that's for the right censored of this light bulb, we don't know when it failed, but sometime in the future. If it's left centered, it means it failed before 5 years, but we don't know exactly when. The intercensoring is just in between. It means it's failed between 2 ion points, but we don't know exactly when. So there are 4 types of censoring data, but for sake of convenience, or maybe this just the standard among literature, we have JMP support 2 types of format. First, we call it right censored format, which I illustrated by these 2 screenshots. If your data only includes failures, you provide a column into JMP, and this column records the time, and this is time to failures. You can supply an extra column, which is this one, example like this one, but here it's the second column does not record time, it records the indicator. It says the time on the corresponding row is a failure or right censored. And combining these 2, this format we call it the right censored data type. And this third screenshot, we have 2 columns. The third column is a count, so it's frequency. The first column are both recording time. But you see that some are the dot. Dot in JMP means the missing value. So for some row, like first one, it's there's dot on the left and there's number on the right. This indicates this observation is left censored. We don't know the time on the left. If we have, for a second row, we have 2 different values on the left and on the right. This represents intercensoring. And let's see the fourth row, you have a number on the left, but a missing value on the right. This indicates a right censoring. If you happen to have 2 numbers on a single row, but 2 numbers are same, this represents a failure. So this is, we call it a 2-column format, and it supports all these 4 types. If we use this right censored format, it can only represent either failure or combination of failure and right censor. So these are the difference. And this slide just summarizes what I just said. So I'm going to skip that. When you launch a JMP platform, if you have used JMP in the past, there's a JMP platform launch dialog. And this is how to specify dialog using these 2 different formats. If your data is all failures, then you just put your time column into this Y, time to event box. If you have 2 columns, first is time, the second one is sensor indicator. You put the time into Y and the sensor indicator into sensor. You have 2 columns of times, then you specify this way. You put both columns into this Y. This is how to use JMP for these 2 different type of data formats. These slides are almost identical to what the instructor put on their slide yesterday, and they are from the same source, the Meeker book. So you have, for the Bayesian method, you have your data, you have a model. If you are a frequentist, you are good to go. You just combine them, get your likelihood, and off you go, you got the MLE, maximum likelihood estimates, and you're done. For the Bayesian, you have to supply a prior distribution for the parameters in your model, which is theta, and combine the prior distribution and the likelihood using a Bayesian theorem and derive what's so-called posterior distribution of theta. From there, you can make other inference. But I put black box here, and what's in the black box? Black box is a computational engine to conduct a Bayesian analysis, Bayesian inference. There are different things can be in this black box. You have different choices, and there are different implementations. So it can be something as simple as so-called rejection sampling method. Or as the instructor mentioned yesterday, it can be a bugs Bayesian using Gibbs sampler. Or it can be a so-called Metropolis-Hastings algorithm, random walk MH method. And in the past maybe 5 to 10 years, there's some newcomer come here. It's called Hamiltonian Monte Carlo methods. So these are different things, and there are lots of variations. And the researchers make a living by varying them and propose the new advantages and by varying them. So I'm not going down there, but these are 3 methods that I'm familiar with, and I list them here. And certainly there are things I don't know. And in JMP, we implemented 2 of them. In the life distribution, we supply rejection sampling method and the Metropolis-Hastings method. In fit-like bags, we do the same thing too. But for repeated measure degradation, we provide only the Metropolis-Hastings method. If we are familiar with these 3, and you know that the rejection method is very rudimentary, it's very basic. Why do we still provide them here? It's bad because when the rejection rate is high, you're just wasting too much resources to sample it. And it's infamous for the high rejection rate if you use this method. But when the failure are scarce, the likelihood function is not in the familiar shape, a bell-shaped curve. It can be rather flat. In that case, the rejection rate is not that bad. It's not that high. And also, this rejection method, if give it enough time, give it enough resource, it's the only way we can check what's ground truth. It has been tried, it can be tested. We know, give it enough resource, we know what the truth is. This is not true for other methods. As the instructor mentioned yesterday, the other methods have advantages if the rejection rate is high, because they tend to stay into a region that has high probability. What if your situation does not have one concentrated area that have the probability? It will never escape using other methods. In that situation, there are no other way to discover that situation except use a very simple one, very stupid one, rejection sampling. But you need to give them enough time. So this is the one way that I developed my platforms, and this is how I tested it. Okay, now let me start with my demonstration. All right, let me start with first example, life distribution. The example I'm going to give you is called a rocket motor data. So what it records, it's published in a paper in the RAMS conference 20 years ago. It describes the situation. There are over 20,000 missiles in the inventory. And over the time, about 1940 missiles have been fired. Among these 1940 events, 3 of them failed. And the scientists and engineers and whoever designed it worried how many missiles in these stockpiles is already bad. Because when they fire it, they pulled from inventory and didn't fire. And that's a failure. But they worried there are too many of them in the inventory that had already failed. And failure mechanism for this rocket motor is due to thermocycling. So it can be hot, can be cold, can be hot, cold. Some of the missiles have been manufactured just after 1 year. Some have been fired but after sitting in the inventory for 16 years. So it has been through a lot of cycles. So the question is, how many are bad ones in the inventory? So that is the question. And the designers expect the missile to have 1% of probability to fail after sitting in the inventory after 20 years. That's their goal. And their question is, did they reach the goal? Let's look at the data. So what you are seeing is a 2-column format. I have 1 column on the left, 1 column on the right. And the third one is count, how many fired. So there are 105 have been filed after sitting in the inventory for 1 year. Why is right censored? That means it did not fail during the 1 year it's sitting in the inventory. It failed sometime in the future, but it did not happen. So it's right censored. How about the 3 failed cases? For 3 failed cases, I set up the time on the left is 0, and the time on the right is when it's pulled out for the firing. That means it failed between 0 and the time when it gets fired. So for the 7th row means this rocket failed, but it failed between time 0 and 16.5 years when it gets fired. And the 18th serum between 0 and 8.5. And the one is from 0, between 0 and 14.2. There are only 3 of them failed. And these bunch of over 1,900 of them did not fail. Let's see how to analyze data to study the time to failure distribution of this particular missile. So to analyze that, go to Analyze menu in JMP, go to Reliability and Survival, and click Time Life Distribution. And I said, feed these 2 columns to Y, and count to frequency, and click Go. That's it. What are I seeing here? It's, if you are new to JMP or new to reliability, we don't know what you are looking at. Let me give you another example, which is better to illustrate. What if we have enough failures? What should we see? I'm just going to open it, just run it. I'm not going to go into the details. This is different examples, but I'm not going to cover what details. We have observed enough failures. The dots here is a non-parametric estimate of the failure distribution to failures. Here, we are not making any other assumptions. We are not saying it's normal, log normal, or viable. This is non-parametric. We wish to see that these dots, but we don't see any, barely see anyone here. There are 3 dots here. That's it. But if we have enough failures, we should see a path, a trend. And also, you notice that the axes here, they are not linear. And this is log scale, and this is called probability scale. And there are different scale to represent this plot. We can change them by clicking these radio buttons here. This is called probability paper, if you check out the literature. The reason here is that traditionally, the engineers just plot these non-parametric estimates on the different probability papers. Actually, they printed it. They print these dots and draw it on the different types of probability paper. If they spot one particular paper and they see that's a linear trend through these dots, then they can be, how to say, pretty confident that the probability paper they hold in your hands represents a distribution that they can fit this data very well. For here, this probability is called log normal probability paper. And I see a pretty straight line going through all these points. That means log normal will fit this data well. And actually, it does fit well. Let's go back to what we have right here. We just see 3 dots. Let's change the probability paper. What happens if we see just 3 dots here? We can put the line in any way that we want. It can be pretty close, but we can't be certain. Let me fit one parametric distribution by clicking one of the checkboxes here. Let me click this log normal. You see that the line is kind of goes through these 3 dots. It can be up a little bit on the right. It can be down a little bit on the left, but approximately it's still close. So that's a problem. That's we cannot be certain that's a good fit, and so we can check out the distribution on the right. So we are interested in the failure distribution about 20 years. Let me put 20 years on the X, and look at the estimates. So here it says, if I use this model to predict my failure probability at 20 years, it give me about 15% of failures. But look at the confidence interval. It's runs through the 1% all the way through over 50%. That's pretty wide. So if the engineers are interested in this 1% of failures, they are far away from that. So to them, these results don't look good. But they spot something that's, they say, oh, I'm sorry, I need to switch to a different distribution should be viable. Yes, they think this viable distribution fits this well, and you see that the dots are now in the shade. This is better. Oh, this is even worse. If you look at the confidence interval, it's from 2% all the way through to almost 1. So to engineers, that's bad news. But they spot something different. Let me close this. And for viable distribution, there's a parameter called beta. It's called shape parameter for beta. And look at it, it's 8. For engineers, some of the engineers, if they're experienced, they can get hunch about this number should be. And they said, this number is too big. This number is too big, that means the failures are too close to each other. And they expect these failures to spread out, and the beta should go lower than 8. They said, I'm not sure this 8 is correct, the true value that they would expect. And so they don't trust this result. But can they use their knowledge to improve that? Now we have to turn to a Bayesian approach. So to put that information into a Bayesian approach in JMP, now I'm ordering how to place this order in JMP. You go to this result, parametric estimate of viable, and find out this Bayesian estimates. So this is the menu. You need to know how to cook it, and how would you like the chef to prepare that. You have different options. Here, the Bayesian, the viable Bayesian estimate give you 2 things you need to specify. One is information about quantile. And second is the information about viable beta parameters. If you know viable before, you know this quantile is not one of the parameters you usually see. There's a scale parameters, alpha or eta. It's not here. Why? For Bayesian approaches, in Meeker's book, he mentioned that the software providers need to provide a way to solicit information from engineers in a way that they can provide actual information. If I put scale parameter here, they probably don't know much about that parameters. But you ask, what's the failure time of the 10% of them will fail? They can give you some idea. And also that's beta is also the parameter, is also the quantity that engineer can give you some information. So here we provide interface to let engineers give information that they have good chance to give useful information instead of some abstract things like mean and standard errors, standard deviation or normal distribution. It's hard to solicit information from in that approach. Also, we look at the value you need to put in. Let me explain what these numbers are. First, for the quantile, it's a normal distribution. I'm asking information for a normal distribution, which is prior for this quantity. And you specify the information about the 10th percentile of failure by providing these 2 numbers, which one is called lower 99% limit, and the other one is called upper 99 limit. This is normal. Where's the mu and the sigma? Where's the mean and the standard error, a standard deviation? It's not here. It's not on either of them. So this is another suggestion Bill Meeker provided, that you need to let the users to provide the information about Bayesian in the most, effective ways. So here I'm asking particular engineer, how much do you know about the range of this quantity? Give me a range instead of give me a mu and a sigma. That's easier to ask that question, and they may have a better idea about what they need to provide. So here I'm asking the 99% quantiles of this normal distribution at the prior. Okay, the second is all similar. I ask for a 99% quantiles for this normal prior on this beta. Let me see what I need to put in here. So I'm not expert on the information. I'm so copy the information and put it in there. Let me see. I need to put 5 here, the range of the 10th percentile, and I think it's 400. This is how you put your order. What do you want? How to cook it? And 1 and 5 for the beta. And for the first one, it's called weakly informative prior. It's very flat. That means we know little about this quantity. The second one, beta, it's pretty informative. That's it. Now you need to put the button and place your order. Fit the model. It's done. It sampled, I think, 5,000 samples posteriors. And it says use simple reduction. The software designed to do that automatically. If the reduction rate is not that high, it's just go with this simple reduction and produce posterior. If the software observes there's a high reduction rate, it will switch to Metropolis Hastings method automatically. In the report, you will see a copy of priors and a summary of posteriors. You have posterior medians and posterior means, whichever you want. There are different ways to summarize that and use that as your point estimate. You can either use the median, posterior median, or the posterior mean. And to some of the assets, the posterior median is the preferred way to use as our point estimate. And now, let's see. There's also a button that you can export Monte Carlo simulation results. And for this particular one, if we went to the short course yesterday, they mentioned you need to see the diagnostics of the autocorrelations and whether it converges, this kind of stuff. For this particular one, you don't need to, because it's a simple method, simple reduction. It's guaranteed there's no autocorrelation in these examples. All right, I'm not going to do that, but I will show example that you need to check later for degradation data analysis. All right, we have this posterior example here. Now we can estimate our failure rate at 20 years. Remember, we had that almost from 0 to 1 confidence interval on the estimates using that maximum likelihood. Now look at these numbers. So the red one is 0.1 failure probability. It's roughly on the target, what the engineers expect. But it has a confidence interval. The lower is 0.0018, the upper is 0.08. So from this result, using the knowledge that engineer can provide, they are a little off from what they expect, but it's pretty close. And they can make their decision based on this information. They need to decide whether they need to go in to the inventory and check every missiles and replace the bad ones. And for the bad ones, they mean it's not the entire missile is going bad. Only a component, which is the rocket motor, which is only a component, goes bad. So if they want to fix that missile, they just need to replace that motor. But the cost can be high if there are too many is already bad. So this example, first example, I'm going to close that. And let me summarize the takeaway. So use the informative prior if you can when the information in data is limited. And use the parameterization, which is useful for soliciting priors. And use an easy way to specify prior. These are all the things that we provide in this software. And make your life easier to place the order. All right, second example. Oh, you have questions? Oh, okay. Do you have questions from the audience? Okay, I think that's so far so good. Let me give you a second example, which is repeated measures degradation. I think we have 30 minutes, right? Yes, yes. I didn't expect this. This topic is challenging as we are from almost from Iron Age all the way to the landing on the moon. Second example is repeater measures degradation. So what is this data? What's different from the failure data? For repeater measure, I mentioned we have different units in our data, and we have measurements over time on individual units, and there are multiple measurements on it. And there are two types of parameters in this type of model. One is called population parameters, and the other is called unit parameters. Unit parameters are different from unit to unit, but they follow some kind of random mechanism generated from the population parameters. The interest is in the population parameters, and we call this unit parameters. In some literature we call them nuisance parameters. The reason is that if we can get these population parameters, we can always get information about a unit we have never seen in the future. That's what we want. We want to get the idea of the randomness of this unit, not about the only one, not only about the ones we have now. We want to know about the future ones. So that's why we care about population unit, and we don't actually care about the unit parameters. That's actually we observe. And another interest is in the failure distribution at a threshold. We measure this degradation from time to time, but I haven't said when it fails. The fails depends on the definition. And definition is a threshold when this degradation curve hits that threshold. That's when it's hit, that intersection is its failure time. So we are interested in the distribution of those intersections. So this is second interest. So the example is alloyed A data. It's a metal freak data, metal fatigue data. What do you see here if I open it? You see the first column is length, the crack length. The second column indicates unit. The different number indicates different unit. And milliamp cycles. So this at the beginning, they all start at 0.9 inches. And over the time, 0.01 million cycles, they measure the first step specimen, and the crack length grows to 0.95 inches. And at 0.02 million cycles, they measure this first specimen, it grows to 1 inch crack, and so on and so forth. And how to analyze this data? Go to Analyze menu in JMP, or the way find out reliability and survival submenu, and find this repeater measures degradation. Put the length, which is our response, which crack length to Y, specimen to system ID, and million cycles to this time. So Y, which is the length our response, time is million cycles, X labels system ID is a specimen. Click OK. If I turn off these curves and connect these dots by unit, you see these are the curves that I measure on individual units, and it goes up. Sometimes it's curled up, sometimes it just goes straight. But eventually, we are interested in when these curves hit this 1.6 inch threshold, and the intersection of this curve with this threshold is the failure time of these individual units, and we want to estimate this failure distribution. Let me go back, toggle this off, and toggle this on. The software gives you an initial fit of this data using this model. This model is not what we want. This is the thing about using this platform. You need to know your model. Assume that you know this model. I'm not going to tell you which model it is. It's down here. Let me scroll down. It's this scary looking model. It's a differential equation, but it happened to be the model that can fit this data. To fit this model, just click this radio button, and this is initial fit. Okay, so this is the first step. You place your order, and now click this button. Go to Bayesian estimation. What do I know now? let's look at this. This is a picture of the solution of this ordinary differential equation. I have two solutions based on the value of B2, but you don't need to know now. You just know this is a solution and this is a model. This whole scary thing is how to specify priors. Do you need to go down deep to specify individual of them? For this case, you don't. And you are ready to order. Just click this button, fit model. Why? The default value setting here is what they mentioned, they refer to as a weakly informative prior. It's very flat. That means there are little information contained in this prior. By this, it's pretty safe that you just go ahead by assuming you don't know anything about it. So this is why you can just, right now, click this fit model button and go ahead. Say it again. Okay. So the question is why it tells the user it's a weakly informative prior. It did not. I placed there, and I can give you the confidence that it's a weakly informative prior. The way of doing that, so that's why I don't want to go to the arguments that I put on the slides yesterday. You should not specify a prior after you're looking at the data. I actually put these default values there after looking at the data. But in a way that I can be very confident that I'm not cheating. You see those initial values? I draw those graphs, those curves up here. Those are what I call initial models. Based on that, I can get a sense of the range of these parameters can be. So that is the initial estimates of what these parameters can be. Then I expand it. I make it flat. By doing that, I make a much weaker informative prior, starting from looking at the data. So if my initial estimate has concentrated information about these parameters, by doing what I have, by expanding it, making the distribution more flat, I make the prior much weaker. So that I'll say that after looking at the data, after doing what I did, the default value I put here is to represent very weak informative prior. And it's pretty safe that you just go ahead and click the fit model button. And now done. So now you have a copy of the prior as I did in the past. And I have a summary of the posterior for the population parameters. Now you need to check the diagnostics. And here are two buttons. I'm only going to click the first one. And there are many columns here. The first several, 1, 2, 3, 4, 5, I think 6 columns. These are the columns for population parameters. And many times we don't want to look at the rest. But you need to look at the diagnostic plot of the first 6 ones here. First is trace plot they presented yesterday. You can run, there are embedded script here. For the first script is a trace plot they mentioned yesterday. By clicking these green buttons, we use a time series platform in the product, and it draws the trace plot, what they mean. It's the same thing. They call it a caterpillar plot. If you see the dots across a horizontal line, wiggly up and down, and you also expand this outline node, it will show you the so-called autocorrelation function. And autocorrelation function is 1 at 0 and almost 0 at 1 and all the way to the bottom. That means in these posterior samples, there are almost no autocorrelation. So you see how easy it is. By starting from doing nothing on the prior specification, and you get the posterior that almost has no correlation at all. And the method I'm using here is match policy Hastings method. There will be autocorrelations if they just go through the steps that the instructor gave you yesterday. And you need to do the thinings and burnings, all kind of stuff. The software that we provide here has taken care of that. And it's all hidden here. You can tune it, but you don't have to most of the time. It's already taken care of burning and and thinning. So you can get a posterior which have very little autocorrelation. So comparing to how you learn to fish and how to just place order your dish, this is comparison. It's easy. Now let me go one more step to finish before finishing that. We want to estimate the failure probability of this metal fatigue data. Go to this, no, not this one. This is outline for the entire model, but we can specify different priors and fit different Bayesian models. We want to go to the outline node of this one. The Bayesian estimate number 1, this is the first model that we fit for this, first Bayesian model fit for this crack length degradation. Click the triangle and click Show Life Distribution Profiler. Our definition failure is 1.6 inches of crack length. When the crack length reaches that point, that means this specimen failed. Click OK. So this now is computing things based on the posterior sample we collected and calculates the failure distribution. And here it is. You can use it as I showed you in the previous examples, and put in the milliamp cycles here at X and read off the probability on the Y, on the side. All right, this is the second example. Let me see how much time we have. 15 minutes plus. So I think I'm on schedule. Let me summarize the takeaway. So when you have nonlinear models, that's pretty scary, ordinary differential equation models. And we have population parameters and unit parameters. When you have these two types of parameters, there's another term that you might have heard during the conference. It's called mixed effect models. When you do the DOE, where that's the most scary part. Let's say if you want to go there, mixed effect models, they have these kinds of situations, population parameters and unit parameters, plus and or have sensory. If we combine all these monsters together, frequentist does not have a straightaway answer. And Bayesian, it's very straight, as long as I can provide a weakly informative prior, and it's pretty easy. So use a weakly informative prior such that the posterior is nearly proportional to the likelihood. The result will be very close to what frequentists could have done, but they can't. So this is one of the takeaway. And jump implications try to take care of deciding the burning and the thinning, so you don't have to worry about effective sampling that, like they mentioned yesterday. Okay, so this is the second example. Let me wrap up. Second one. So this is FitLife by X platform. It's for accelerate life testing data. So the data set here is an integrated circuit board device. And because it's a semiconductor product, it's pretty reliable. And to break it, it's so hard. But the engineer figured out a way to put it under different temperatures. And so like, let me see. So the experiment is under 150 degrees C, 175, 250, and 300 C. So the way of doing that is they try to observe failures at high end of the temperature, and their use condition is 100 C. So they can extrapolate backward to find the distribution at 100 degrees C, which they will never observe any failures within the duration of the experiment. And they are interested in the failure probability at 10,000 hours on the 100 degrees C. Let me open up this data set. So it has, let me see. Again, this is 2-column format. We don't use these sensoring indicators because we have this 2-column format. This is count, which frequency. And this is a condition that each unit is under what condition. To analyze that, go to Analyze menu, Reliability Survival, and the FitLife by X. We put the 2-time column to Y, count into frequency, degree C into X. Now you need to decide which acceleration mechanism you need to apply. Here it's called Arrhenius Celsius. So this is Arrhenius relations using the Celsius unit. If we are into this subject, you will know that Arrhenius is very commonly used relationship for temperature-related acceleration. And if I click this combo box, you will see this is more than I expected. So I said 8, and now it's more than 8 now. So we provide a different mechanism for modern different kind of acceleration mechanisms. But for here, Arrhenius Celsius is good enough for us. And I'm going to click OK. The data only have failures at 250 degree and 300 degree. And again, we have a 3-dot situation. So we at least know that the problem. We have very few failures. Turns out it has another problem here. It's getting worse. The failures at 300 degrees C, the engineer find out the failures here will, the mechanism that it fails here will never occur when if they run on under 100 temperatures, 100 C temperatures. These they call different failure modes. And this failure mode is so extreme because the extreme heat temperature, 300 Celsius. And this failure mode will never occur if they put this unit under 100 degrees C. What if we leave the data here? It will bias our, mislead our conclusion or result. So we have to remove that. What will happen if we remove that? Let me remove it. So it's 300. Let me right click in a cell and choose select matching cells. I'm selecting all the rows associated with 300C. And then right click and say hide and exclude. Let me relaunch it and click this button recall. So I don't have to do anything, just a simple recall. Okay, now you see that says 200 degrees, 250 degrees, it has failures. What's wrong with that? Remember we have these Arrhenius models? After fitting Arrhenius models, that we should be able to extrapolate our distribution at 100 degrees C. How to extrapolate that? Let me turn on some additional elements in this graph. I'm going to turn on add quantile lines, click OK, and turn on the density curves. I'm not going to explain how do I get it, but to give you an impression how we extrapolate that. So after fitting this model, we will be able to draw these straight lines. And at any given temperature, we will be able to draw this density curve. I'm going to add a 100 density curve here. Add a density curve at 100 degree. This particular density curve is what I can get after fitting this model. It seems pretty good, but there's something wrong with it. Because we don't have any failures here, the straight line here is not reliable. Intuitively, that we can put this line anywhere as long as this portion of the line is above these observations. That's a problem. We don't have enough. If we want to draw a straight line, we have to get 2 points to fix it. But here we don't have 1 point. We only have a point at this end, but we have a suitable point over here. That's why, even if we can draw this line, if we put some data in the software, it will crank some numbers give you the report. But there's something wrong with these numbers, and we can observe that by looking at these things. We put 100 degrees C in this probably this profilers and put, say, I think that's 100,000 hours. And read off the numbers here. They give you the number, a prediction, pretty small. But confidence interval is 0 to 1. It's useless. You don't have any confidence about the estimation. So But after engineering expecting the failure mode, they conclude this result is not reliable. And by looking at the result, the conclusion is not reliable. But the engineers know something about it, the statisticians don't. And in Arrhenius relationship, there's a parameter called activation energy, which is the B1, beta 1 here. It's related to acceleration, Arrhenius relationship. And in many situations, they know something about this number. They know a range about it. Let's see how to put this information into there. I'm going to do that. That we needed the Bayesian approach again. To do Bayesian approach, click this tab, Bayesian estimation. I need to use my cheat sheet and put in the numbers. Oh, by the way, again, the parameters here, the quantities here are not the parameters naturally what you will see in the model, beta 0, beta 1, and sigma. Here, the first one is the quantile. The second one is activation energy. The last one is sigma, which is the scale parameter for the log normal distribution. So what's the number that I need to put in? So activation energy is 0.8, 0.95. Again, this is the range. This is not asking for mu and sigma for the normal distribution. For the sigma, I'm going to put 0.0625 all the way to 16. And let me see, quantile, this is 200 degrees C, 0.1 probability, and 100 to 32,000 hours. So by doing this, this is a weakly informed prior for quantile, and a weakly informed prior for sigma, and informative prior for beta 1. Oh, by the way, I need to turn this into log normal. So this is the prior that engineer provide, so I can specify it. That's it. Click the fit model. That's it. And it says the method is simple reduction. I don't have to worry about the autocorrelation, something like that, and just go straight ahead. Scroll down, and here is distribution profilers. So we can get our estimates at 100 degrees C at 100,000 hours, and read off our estimates of the failure probability and the Bayesian credible interval. That's it. That's simple. I have 5 minutes. That's why I reordered my example last night. So I give you all 3 examples, cover 3 platforms. Oh, let me cover this takeaway. So in the accelerated live test, be careful about failure modes, and you can read amazing stories in Bill Meeker's publication. I think it's under the name, if you search for the pitfalls of accelerated live test, you'll find at least 2 articles on this, under this name. And they will tell you how important to pay attention to failure modes in the accelerated type test. And when the information in the data is limited, use informative prior if you can, as I mentioned before. Again, use a parameterization that's useful for soliciting priors. Again, use an easy way to specify priors. And the software that we implemented provide all these. That's why I rearranged my, at least I cover 3 platforms for 3 examples. And the last example, which is repeated measures degradation with 1 acceleration factors. It will be very much close to what I showed you already in the second examples. Except I want to mention this MCMC control I showed you before that. I told you that don't worry about that. That's true for most of the situations. Let me run it. Let me quickly run it. I may need 3 minutes to run it. Let me see. Power job is our Y, device is ID, hour is my time, degree C is my X. So this will be a nonlinear model, and I know the model already. Let me finish running it quickly. provide the things. I'm skipping details. Click Bayesian estimation. Give it a short run, save me some time. Okay. So what's it's running? Let me see. Yeah, now it's starting. So look, pay attention to the dialog. It says step tuning on the second row, and the next row says warming up progress and lap 3 out of 10, 4 out of 10 now. So the software is trying to figure out a best way to explore this posterior. In yesterday's short course, when they put that a posterior, a big curve, a big bell curve, and they put a small bell curve on the bigger one. That's their proposal. And then they decide whether they want to go up or go down based on that proposal, and it calculates the ratio of the probabilities. That's how they explore the posterior. But it's tricky to decide your proposal distribution. That's little bell shape. How wide should it be? That's the key. If it's too narrow or too wide, neither are good. Neither will cause high autocorrelation. That means you're exploring that posterior very slowly. So we have to tune a proper scale for that little bell shape. And this is what they're doing in the first stage. Now it's the second stage. Okay, so the first stage is trying to figure out the size of that little bell shape on that bigger one. And also it's find out how much thinning I want to apply so I can minimize autocorrelation. That's all happening in the first stage. Now it's in the second stage. It decided what's the shape of little bell shape and what's the gaps I need to thin this posterior. And now it's actually doing that. Let me see, it will spend 3 minutes. I think it's a good time to ask questions. We will wait anyway. Okay, no question. That means I'm doing a good job. So if we're looking, while we are waiting, look at the MCMC controls outline node down there. So you can see there are not many boxes you can change. So what they do? So first one is the warm-up laps. As I mentioned, if there are, I will show you an example. That's what do they mean by autocorrelation? I will show you. After this one, you will see that there's a little bit of autocorrelations in the posterior. And if it's not too bad, just accept it. But if too bad, you have a couple of things you can change here. First one is warm-up laps. The default is 10. In all the cases we had tested, it's pretty good. I have never had a need to go up, say, beyond 50 laps in all the cases I've tried. So that's one thing you can change. If you see some convergence issues, when you see convergence issue, I mean that you see that posterior trace plot, instead of seeing caterpillar, you see a stock market. It goes all the way down for a while and goes all the way up to for a while. That kind of plot, that means you have convergence issues. And you will absolutely see not comfortable by taking that as your posterior. If you observe that, one way to improve that is to try to increase that warm-up laps. So it will be harder to figure out the size of that little bell shape. And if you get lucky, it will converge. The other thing actually you can change is that you are observing that caterpillar plot, but the autocorrelation functions still show you that there's some long autocorrelation, say up to 10 lags, something like that. In that case, you are already sure that it's converged, but you still need to thin it a little bit harder, or a little bit, give it a little wider gap to thin it. Uncheck that auto thinning checkbox. It's finished. So in that case, uncheck this box and put a desired thinning number here to increase the thinning, to improve that the posterior's autocorrelation. Let me give you a taste what that autocorrelation look like. So know which one has a little bit of correlation. So this is the one. This is the B3 parameters. Even I have applied the thing. This is thing applied. That's 924. I'm already seeing it. And by looking at these plots, these are beautiful caterpillar plots, and it's converged. But you still have autocorrelations. And for this particular one, it's pretty good. You can just accept this as a result and report the final inference. But if you're not comfortable with it, just go uncheck this box of thinning and say put it at 2000 there to run again. So these are the two tips that's to address that kind of concern. But software has already tried very hard to address that automatically. Okay, I think it's right on, a little bit off. Thank you, guys. Thank you. Thank you.